Hi everyone. In this particular video, we are going to talk about definition of metric spaces, and we'll not stop with merely the definition. We'll look into understanding it in detail, and for that we'll make use of examples, counterexamples, challenges, detailed challenges, questions from different sources, established sources, and through this process we are going to try understand this one definition of metric spaces, which is mostly in your classrooms, taught for 5 minutes and left off by your teacher. And to understand this definition, the only prerequisites that I ask for is the definition of sets, functions, and an open mind to learn something new. Sets and functions are taught to you from the school level. So even if you're a school student and has an open mind to learn, this definition is something you can easily understand. Neil deGrasse Tyson is one of the famous astronomers of the day. He is also well known for his skills in science communication. Science communication is a field where you talk science in a way that commoners can understand. Advanced topics in science in a way that commoners can understand. So, Neil deGrasse Tyson said something interesting. He said, science literacy is not so much about what you know, but about how your brain is wired for thought. How your brain is wired to ask questions. Interesting, right? I would say, just like science, that's the exact thing that you should develop as a mathematician. Mathematics is not about how well you memorize the definition or how well you memorize a theorem, but about how well are you equipped to understand the definition? How well are you equipped? What are questions do you ask a definition to understand it better? How well can you understand a theorem when it's presented to you by yourself? How well can you formalize a concept? That is, if you're given an intuitive idea of a concept, how well can you formalize it and write it down as a definition? These skills are the skills that you should focus on developing as a mathematician, and in our videos that'll be exactly the skills that we will be aiming at developing in you. To give an outline of what we are going to go through in this video series, we'll start with definition and meaning, which will be the focus of this particular video. Then in the subsequent videos, we'll be looking at examples, counterexamples, a few challenges, and some extra challenges. Why do challenges and extra challenges? In challenges, the questions are going to be easy. In extra challenges, it may be the same questions, but I'm going to word it in a tricky way so that it trains you to apply the definition we are learning in context of the problem given to you. And then we'll look at some CSIR net questions. It's a reputed question source, and we will see how our understanding of definition so far is going to help us solve questions faster. In the end, we'll summarize all the learning in this section, including all the examples, counterexamples, facts that we noticed in the summary section. And also, I'm not going to stop with that. I'm going to give you some more detailed definitions, detailed examples and counterexamples, which will help you understand this definition better. But those examples are going to be a little advanced, and I hope by the time we reach that section, you'll be an expert to understand them easily. And then we'll also provide some extra reading materials to help you start off your research with about this particular topic. Let's start with definition and meaning. The definition of metric spaces, as I already told you, doesn't require anything extra than the idea of sets and the idea of functions. So, to quickly recollect the idea of functions, there's an interesting book called Bartle and Sherbert, and the book is titled Introduction to Real Analysis. And in the book, the authors claim that a function can be viewed as a machine where you put in something and you get some other output. For example, suppose there is a machine where you put 2 and you get 4. You put some other number like 3 and you get 9, and 4 and you get 16. trivial, right? For a mathematician, he would have thought, why is he calling it a machine? It's f of x is equal to x squared. So a function can be viewed as a machine where you put in some values and you get some other output. So this particular set of values that you are allowed to put into a function, that set of values is called the domain, and this particular set of values that you get as output, that set of values is called the range of the function. And this range can be contained in any bigger set. Any bigger set which contains range can be the codomain for the particular function. You should already be familiar with it since you would have studied it in your school, maybe. So let's start looking at the definition. To begin with, to define a metric space, what we need is a non-empty set M. Only condition on the set is it should be non-empty. The reason we are assuring that it's non-empty is if it's empty, our study is trivial. Hence, let's keep it at non-empty. We are going to need a particular function rho, and this function is going to be called a metric for M if it satisfies a certain set of conditions. First condition, domain should be M cross M. 2. Range should be contained in closed interval 0, infinity. Very peculiar, right? Those are aware of the idea of codomain. Why are they not saying codomain should be 0, closed interval 0, infinity? They are simply saying range should be contained in 0, infinity. We'll see why is it so in the challenges section in detail. Along with these two conditions, it should satisfy 4 numbered conditions. First, rho of x comma x is equal to 0 for all x belongs to M. 2. Rho of x comma y is greater than 0. That is, rho of x comma y should be positive for every x and y belongs to M and when x is not equal to y. Third condition, rho of x comma y is equal to rho of y comma x. That is, even if the input x and y are flipped, the function doesn't change its value for every x and y belongs to M. Looks like flipping has something to do with symmetry, right? When something doesn't change even when you flip, that means it is symmetric. That's a real world concept. So it has something to do with symmetry. Now, the fourth condition is the toughest. Although it looks like the toughest, it may be one of the easiest once you understand what it is. It says rho of x comma y is less than or equal to rho of x comma z plus rho of z comma y. And it is called triangle inequality. We know what triangle is, but this looks nowhere near a triangle for sure. Now, this particular function rho, if it satisfies these conditions on domain, range, and these numbered conditions, then we would call it a metric for M. If it is a metric for M, then the ordered pair M comma rho is called a metric space. Notice that rho is a metric for the given set M, and all our conditions listed here is dependent on what this M we choose to be is. Again, a peculiar question. I told you this is going to be a beginner video which can be understood by a school student. But this is a lot of math out here. What exactly is happening? Why is it? It looks a lot tough, right? Now let's try to understand what exactly this definition means. To begin with, let's try to take hints from the definition itself. We are defining something called metric spaces. Why did they choose this word metric for this particular definition? It's going to be a space. Okay, well and good. Why did they choose to call it metric spaces? So I just quickly Googled. I went to Google and typed metric definition. And then this is what Google told me. Metric, adjective. If you notice the first meaning here, it says related to or based on the meter as a unit of length. Peculiar, right? It's relating to or based on the meter as unit of length. Meter is a distance. Meter is a measure for distance. And turns out it has something to do with distance then. Let's take a look at the definition again. We know that if you stand at the same point, the distance traveled is 0. Take a look at the first condition once more. If you stand at the same point, the distance traveled is 0. I can only walk a positive distance. I can only walk a positive distance. I cannot walk a negative distance. Very interesting. This seems to have something to do with the idea of distances. And turns out this is nothing but the idea of distances that we have in a real world in terms of in mathematical language. Let's see how it is. 1. We know that a distance from a point to itself is 0. Consider the point x, and I'm going to stand at x. Turns out the distance I've traveled is 0. Now take a look at the mathematical formulation once more. Rho of x comma x is equal to 0. Let me read it once again in a slightly different way. Distance from x to itself is equal to 0 for all x belongs to n. Whoa, this seems to match. Let's look at the second one. Before we proceed to the second one, let me make a small note. When you're going from x to y, you can go in different ways. You can either walk the straight line like this, or you can walk from x to somewhere else and then take a turn, take a left, right, and keep taking turns to reach y. But since we are trying to understand the concept here, and since we are trying to formalize it into mathematical terms, let's consider the simplest possible case of when I say distance, what I mean is the straight line distance between those 2 points. With that in mind, let's continue to the next condition. Second condition says rho of x comma y is greater than 0. We know that going from x to any other point when x is not equal to y, we are always going to travel positive distance. Even if we are going from y to x, we are always going to travel a positive distance. We cannot travel a negative distance. It's highly intuitive idea. Hence, second condition also seems to be something like writing down property of distance in mathematical terms. Third condition, we know that going from x to y, suppose I'm standing at x and someone else is standing at y. When I walk from x to y and that person is walking from y to x, we're both going to travel the same distance. And it's highly intuitive and trivial. And as we already noticed, flipping the input here of this particular function doesn't change its value, and it has we already told that it has something to do with symmetry. Now the final condition, triangle inequality. As we did with the definition, let's take a hint from this particular name of triangle. It has something to do with the triangle. Let's see how. And as I already told you, it's kind of scary because the first condition talks about equality, second condition talks about greater than, third condition talks about equality again. They all dealt with at most 2 input to x and 2 variables x and y. Turns out in this condition there is a third one, z. So this should be the most complicated one in the entire list, right? Soon you will see that it's not. So we have to take x, y, and one z, and we know that walking from x to y, I want to go from x to y, I can take two routes. One, either walk straight or walk to z and then from z to y. Highly intuitive that the shortest route from x to y is nothing but going from x to y straight instead of going from x to z and then to y. Let me read it again. Distance from x to y straight is shorter than distance from x to z and then going from z to y. If you notice trivially, this looks like a triangle, right? Now you can guess why it is named triangle inequality. But then there is a small question that I have. Why do you think we need less than or equal to? If you see this picture, it's clearly less than. Distance from x to y is clearly less than distance from x to z plus distance from z to y. Then why have they given less than or equal to? That case arises when you have z lying between x and the straight line distance between x and y. In that case, distance from x to y will be equal to distance from x to z plus distance from z to y. So that is why they were very careful in putting less than or equal to here. Now, we just noticed that this definition of metric spaces is nothing but rewriting the idea of distances in mathematical terms. And this process of rewriting a real world idea in mathematical terms is called generalization. And a mathematician named John Mason said, generalization or abstraction is a heartbeat of mathematics. If teachers are unaware of its presence and are not in the habit of getting students to work at expressing their own generalization, then mathematical thinking is not taking place. So, first of all, he says it's a heartbeat of mathematics. Skip a beat and it can cost your life. Maybe it can cost your life. And a student in a mathematics class should be trained to generalize concepts in mathematics rather than just by hearting or rather than just memorizing a set of definitions and theorems. And that's a real joy of learning pure mathematics. Also, why do we choose to write generalizations in mathematics? One of the famous mathematicians, I think it's Galileo, who said, mathematics is the language with which God wrote the nature. The reason he said that is, nature is so perfect and beautiful, and it has to be written with a language which is close to perfection. So, pick any language in the world. There is no language as beautiful and as perfect as mathematics in expressing the ideas. Maybe that's why he thought mathematics is the language with which God wrote the universe or the nature. So, we are all students of that beautiful subject called mathematics, and we can be proud of it. And while we are proud to call ourselves mathematicians, we should also train ourselves to be good mathematicians. And it's not your teacher's job to teach you so, it's your job to develop such a mathematical thinking. And I hope in the future classes we'll be able to train you to think like a mathematician, to create ideas like a mathematician, to write down your observation, your thoughts, the concepts that you develop in your mind into mathematical terms. With that, let me conclude this video. In this particular video, we simply looked at the definition and we looked at where that definition came from. We've noticed that the idea of distance that we all know, and the idea of metric that we just defined seems to be one and the same. And this process of rewriting real world idea into a mathematical object is called abstraction. And we noticed how important abstraction is. But if it's talking about the same thing as distance, why do we need to abstract an object called metric spaces? We will soon see that there are many other functions which obey the idea of distance we abstracted, other than the real world distance we know of. And that, in fact, I'll also be claiming that we are all superhumans as mathematicians, because we do things that physicists will take few hundred years to achieve. Watch out for the next video to know more about it. With this, I conclude. Subscribe to the channel to know more to get live updates of the videos posted in future. And you can also subscribe to the channel Christie's Classes, links of both of which will be displayed to my left, to learn more about and develop your general aptitude thinking, to solve more puzzles in general aptitude. Thank you for watching. Please don't forget to subscribe.